Hey there, universe nerds. When we think of the early universe, we picture the bright Big Bang or the first stars blazing to life. But there was a time in between, a time of pure darkness, when no stars, no galaxies, not even light filled the skies. Astronomers call this mysterious chapter the Cosmic Dark Ages, and it lasted for hundreds of millions of years. Today we're exploring what happened during this shadowy period, why it was so important, and how it set the stage for the universe we see today. The Dark Ages began about 380,000 years after the Big Bang, right after the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before that, the universe was a hot plasma, glowing with light. But once atoms formed, the light could finally travel freely. That glow is what we now see as the cosmic microwave background, or CMB. After that moment, the universe went dark. With no stars or galaxies yet, there were no new sources of light, only endless hydrogen fog. For millions of years, the universe was quiet. Gravity was slowly pulling hydrogen together into clumps, but nothing shone yet. This era was like cosmic waiting time, silent, invisible, and crucial. The only activity was dark matter forming gravitational wells, pulling gas into regions that would later ignite as stars. Without dark matter, structure might never have formed at all. The first sparks of light came from population 3 stars, the very first stars in the universe. These stars were massive, hundreds of times the mass of the sun, burning hot and bright, but living short lives. Their light ended the Dark Ages and began the epoch of reionization, when ultraviolet light from the first stars and galaxies stripped electrons from hydrogen again, making the universe transparent. But before that, in the true Dark Ages, everything was still hidden. So, how do we know anything about this dark chapter if no light escaped it? Astronomers use indirect clues. One is the CMB itself, which carries imprints from just before the Dark Ages. Another is the faint signals of neutral hydrogen, especially the 21-centimeter line, a radio wave emitted when hydrogen atoms flip their spins. Detecting this signal across cosmic distances could map the Dark Ages, though it's incredibly challenging due to interference. The Dark Ages are also a playground for bold theories. Some suggest that exotic physics, like dark matter annihilation or early black holes, might have added faint glows during this era. Others wonder if inflation left subtle patterns we could detect. If we can study the Dark Ages more closely, we might learn not just about the first stars, but about the fundamental nature of matter, energy, and even the fabric of space-time. Modern telescopes like the James Webb Space Telescope and future projects like the Square Kilometre Array are designed to peer as far back as possible. Webb is already finding galaxies from just a few 100 million years after the Big Bang, right after the Dark Ages ended. The SKA may someday detect those elusive 21-centimeter signals directly, giving us a map of the cosmic dawn. Each new observation brings us closer to illuminating the darkness. What's humbling is that the Dark Ages lasted far longer than our entire human history, yet we can only glimpse them indirectly. They remind us that the universe is not just about light, but about silence and waiting too. Without this quiet era, stars and galaxies would never have formed. The Dark Ages were the womb of the cosmos, nurturing the seeds of everything we see today. So, what were the Dark Ages? They were the universe's long pause between the glow of the Big Bang and the first stars. A time of hydrogen fog, gravity's patient work, and unseen preparation. Next time you look at the night sky, remember, before the stars lit up, there was a vast, silent darkness. And out of that silence came the first light.